So how we write the electrons configuration of elements? Let's look at these two examples. Write the electronic configuration for the following elements. Carbon, which has 6 electrons. Chlorine, which has 17 electrons. First, carbon. It has 6 electrons. Its electronic configuration is 1s2, 2s2, 2p2. Secondly, chlorine atom. 1s2, 2s2, 2p6, 3s2, and 3p5. Usually, we abbreviate the electronic configuration. For example, we use neon that has 10 electrons, and instead of writing 1s2, 2s2, 2p6. Argon replaces 18 electrons. Krypton replaces 36 electrons. Back to our example. For chlorine, instead of writing the long chlorine electronic configuration, we can replace the 10 electrons with neon. So we write neon 3s2, 3p5. We often use energy level diagrams to show the arrangement of electrons in orbitals in order of their increasing energies. Here is the energy diagram for carbon on the left. From the diagram, you can see that the orbitals are arranged from down to top in order of increasing their energies. 1s2, 2s2, then 2p2, according to Aufbau principle. Also, you can see, according to Pauli exclusion principle, we paired the electrons in 1s and 2s. Finally, you can see that we followed Hond's rule by singly filling the p orbitals before pairing, and that the spins of the two electrons are in the same direction. Now, try to see how did we apply the 3 rules in chlorine energy diagram. Let's learn more about the energy of electrons and the factors that affect electrons in each level. The net charge of the nucleus is positive, which makes it hold tightly to the nearest negatively charged electrons. The attraction of the opposite charges, nucleus and electrons, is the most in the energy levels nearest to the nucleus. Going further from the nucleus, the electrons in each level are affected by the repulsion between electrons. If we go back to the energy diagram of carbon and apply these concepts, first, the electrons in the lowest energy orbital, 1s, are held tightly to the nucleus. It takes a large amount of energy to remove electrons from the 1s orbital. The energy exerted to remove the electrons, we call it the ionization potential. So the ionization potential of 1s is extremely high. Going away from the nucleus, electrons in 2p have the lowest ionization potential and much easier to be removed. Another 2 terms we need to be familiar with. Electrons in the left diagram are in the ground state. We mean by the ground state the original state of electrons without applying any external factors. Giving energy to an atom makes electrons transfer to what we call excited state. In the example on the right, the carbon atom is in the excited state, in which one electron from the 2s gained energy and moved to 2p vacant orbital. Now, the atom is in the excited state. Usually, the electron in the excited state makes the atom unstable. That is why the electron returns to its ground state and energy is released.